Hello there, and welcome to the Sleepy Science Society. Tonight, we're embarking on a quiet journey through the ancient story of our planet, written in layers of stone and whispered through the slow movements of continents. Geology is the science of Earth itself, the study of rocks and minerals, mountains and valleys, earthquakes and volcanoes. It's a discipline that asks us to think in timescales so vast they challenge our imagination, where a million years is merely a brief moment in the planet's long biography. As you settle in for this gentle exploration, I invite you to let the rhythm of these geological stories carry you into relaxation. If you find comfort in these quiet journeys through science, consider liking this video or subscribing to the channel. It helps others discover this peaceful corner of learning, one sleepy soul at a time. But for now, all you need to do is rest. Let your breathing slow. Allow your body to sink deeper into comfort. Let your mind drift through the deep history of Earth. Geology reveals a planet that is anything but static. Beneath the seemingly solid ground, immense forces are constantly at work, reshaping continents, building mountains, and carving valleys. The rocks beneath our feet carry stories that stretch back billions of years, preserving evidence of ancient oceans, vanished mountain ranges, and life forms that disappeared long before humans walked the earth. Tonight, we'll wander through these stories, from the slow dance of tectonic plates to the patient work of water wearing down stone, from the explosive violence of volcanoes to the quiet accumulation of sediments on ancient seafloors. Let yourself relax completely as we begin this journey. There's no need to remember every detail, no test waiting at the end. Simply allow these geological wonders to wash over you like waves on an ancient shore, smooth and steady, carrying you deeper into rest. The living planet. Plate tectonics. Imagine Earth not as a solid, unchanging sphere, but as a dynamic body with a surface that moves, shifts, and reshapes itself over immense stretches of time. The theory of plate tectonics describes how Earth's outer shell, the lithosphere, is broken into massive puzzle pieces called tectonic plates. These plates float atop a layer of partially molten rock, moving at rates so slow they seem imperceptible in a human lifetime, yet powerful enough to build mountain ranges and open ocean basins over millions of years. The story of plate tectonics begins with a German meteorologist named Alfred Wegener. In the early 20th century, around 1912, Wegener noticed something curious while examining world maps. The coastlines of South America and Africa appeared to fit together like pieces of a jigsaw puzzle. This observation sparked a revolutionary idea. Wegener proposed that these continents had once been joined together as part of a single massive landmass, which he called Pangaea, meaning all Earth. He suggested that this supercontinent had gradually broken apart, with the fragments drifting slowly across Earth's surface to their current positions. Wegener collected evidence to support his hypothesis. He found identical rock formations on opposite sides of the Atlantic Ocean, matching geological structures in South America and Africa like pages torn from the same book. He discovered fossils of the same ancient plants and animals on continents now separated by thousands of miles of ocean. A small reptile called Mesosaurus, for instance, left fossils in both Brazil and South Africa, despite the creature being far too small to have crossed the Atlantic Ocean. Similarly, fossils of the fern-like plant Glossopteris appeared in rocks from South America, Africa, India, Australia, and Antarctica, suggesting these landmasses had once been connected. Despite this compelling evidence, Wegener's ideas faced fierce resistance from the scientific community. Geologists of his time struggled to understand what force could possibly move entire continents across Earth's surface. Wegener suggested that continents plowed through oceanic crust like ships through ice, but this mechanism seemed physically impossible. Without a convincing explanation for how continents moved, most scientists dismissed his theory of continental drift. Wegener died in 1930 during an expedition to Greenland, his ideas largely rejected by mainstream geology. The vindication of Wegener's vision came decades later, in the 1950s and 60s, through discoveries made on the ocean floor. During World War II and the Cold War that followed, navies around the world mapped the ocean floor in unprecedented detail, seeking to understand underwater terrain for submarine warfare. These surveys revealed a surprising landscape beneath the waves. Running down the center of the Atlantic Ocean like the seam on a baseball was a massive underwater mountain range, the Mid-Atlantic Ridge. Similar ridges were discovered in other oceans, forming a continuous system of underwater mountains that wrapped around the globe like the stitching on a tennis ball. Scientists studying these mid-ocean ridges made an astonishing discovery. The rocks on the ocean floor were youngest right at the ridge and grew progressively older with distance from the center. Even more remarkably, the ocean floor showed a pattern of magnetic stripes running parallel to the ridges. Earth's magnetic field reverses periodically, with north and south magnetic poles swapping places every few 100,000 years. As molten rock emerges from mid-ocean ridges and solidifies, magnetic minerals in the rock align with Earth's current magnetic field, creating a permanent record of that field's direction. The symmetric pattern of these magnetic stripes on either side of mid-ocean ridges provided powerful evidence that new ocean floor was being created at the ridges and spreading outward. This process, called seafloor spreading, finally provided the mechanism that Wegener's theory had lacked. Earth's surface wasn't a single solid shell. It was broken into rigid plates that moved independently. At mid-ocean ridges, plates were pulling apart, and molten rock from Earth's mantle was rising to fill the gap, creating new oceanic crust. But if new ocean floor was constantly being created, where did the old ocean floor go? The answer came from studies of deep ocean trenches, the deepest parts of Earth's oceans, plunging more than 10 kilometers below sea level in places like the Mariana Trench in the western Pacific. These trenches marked zones where oceanic plates were diving beneath other plates, returning to Earth's interior in a process called subduction. As an oceanic plate descends into the hot mantle, it melts and is recycled, its materials eventually rising again as new magma. This explained why ocean floor rocks were never older than about 200 million years, despite Earth being over 4.5 billion years old. The ocean floor was constantly being renewed, created at mid-ocean ridges and destroyed at subduction zones. By the mid-1960s, these discoveries had revolutionized geology. The theory of plate tectonics emerged as a unifying framework that could explain virtually all of Earth's major geological features and processes. The concept was elegantly simple, yet profoundly powerful. Earth's outer layer consists of several major plates and numerous smaller ones. These plates move because of convection currents in the mantle beneath them. Think of it like a pot of thick soup heating on a stove. Hot material from deep within Earth rises toward the surface, cools, then sinks again, creating a circular pattern of movement. These convection currents in Earth's mantle drag the overlying plates along like rafts on a slow-moving river. The edges where plates meet are called plate boundaries, and they come in three main varieties, each producing distinctive geological features. Divergent boundaries occur where plates move apart from each other. Mid-ocean ridges are the most common example, but divergent boundaries also appear on continents, creating rift valleys. The East African Rift is a spectacular example of a continental rift, where the African continent is slowly being pulled apart. Over millions of years, this rift may widen enough to allow seawater to flood in, eventually creating a new ocean basin and splitting Africa into separate land masses. Convergent boundaries occur where plates move toward each other. The outcome depends on what types of crust collide. When an oceanic plate meets a continental plate, the denser oceanic plate typically subducts beneath the lighter continental plate. This process creates deep ocean trenches offshore and volcanic mountain ranges on the continent. The Andes Mountains along South America's western coast formed this way, as the Nazca Plate dives beneath the South American plate. When two oceanic plates collide, one subducts beneath the other, creating chains of volcanic islands called island arcs. The Aleutian Islands stretching from Alaska toward Russia are an example. The most dramatic convergent boundaries occur where two continental plates collide. Neither plate subducts easily because continental crust is too light and buoyant. Instead, the collision crumples and thickens the crust, pushing it upward to create massive mountain ranges. The Himalayan mountains, Earth's tallest peaks, rose from the collision of the Indian plate with the Eurasian plate, a collision that began about 50 million years ago and continues today. Transform boundaries represent the third type of plate boundary, where plates glide horizontally past each other. These boundaries don't create or destroy crust, but they generate powerful earthquakes as the plates grind past one another. California's San Andreas Fault is perhaps the world's most famous transform boundary, marking the place where the Pacific Plate slides northwestward past the North American Plate at a rate of about 5 centimeters per year. The driving force behind all this movement is heat from Earth's interior. Some of this heat is left over from Earth's formation 4.5 billion years ago, when countless collisions of space debris generated tremendous temperatures. Additional heat comes from the radioactive decay of elements like uranium, thorium, and potassium in Earth's interior, a process that releases energy steadily over billions of years. This heat causes the mantle to flow, and while the mantle is solid rock, over geological timescales it behaves like an extremely thick, slow-moving fluid, flowing at rates of perhaps a few centimeters per year. The theory of plate tectonics has transformed our understanding of Earth. It explains the distribution of earthquakes and volcanoes which cluster along plate boundaries. It accounts for the location and orientation of mountain ranges. It illuminates why certain types of minerals and ore deposits appear where they do. It even helps explain patterns in the distribution of ancient life forms, showing how species could spread between now separated continents when those land masses were joined. Plate tectonics is geology's unifying theory, the framework that makes sense of countless observations and ties together the planet's geological phenomena into a coherent story. The rock cycle, Earth's endless transformation. Rocks are not eternal. They transform from one type into another through an endless cycle powered by Earth's internal heat and the energy from the sun. Understanding this rock cycle reveals how Earth continuously recycles its materials, turning mountain ranges into sand, sand into solid stone, and stone back into molten rock that will eventually cool and solidify again. Geologists classify rocks into three main categories based on how they form: igneous, sedimentary, and metamorphic. Each type tells a different story about the conditions and processes that created it, and each can transform into the others through various geological processes. Igneous rocks form when molten rock, called magma, when underground, and lava, when it reaches the surface, cools and solidifies. The word igneous comes from the Latin ignis, meaning fire. These are Earth's original rocks in a sense, the first solid material to form as our planet cooled from its initially molten state. Even today, igneous rocks continue to form wherever magma reaches the surface through volcanic eruptions or cools slowly beneath the ground. The key factor determining an igneous rock's texture is how quickly it cools. Magma that cools slowly, over thousands to millions of years deep within Earth's crust, allows crystals time to grow large. A scientist named Norman Bowen studied how minerals crystallize from cooling magma in the early 1900s, developing what's now called Bowen's reaction series. This describes the order in which different minerals crystallize as magma cools. Minerals rich in iron and magnesium, like olivine, form first at the highest temperatures. As the magma continues cooling, other minerals crystallize in a predictable sequence, ending with quartz, which forms at the lowest temperatures. Granite exemplifies an igneous rock formed from slowly cooled magma deep underground. Break open a piece of granite, and you'll see it's composed of visible mineral crystals interlocking like a three-dimensional jigsaw puzzle. The different colors represent different minerals. Milky white or pink crystals are feldspars, clear glassy crystals are quartz, and dark flakes are usually mica or amphibole. These large, visible crystals indicate the magma had plenty of time to cool and allow crystals to grow. In contrast, lava that erupts at Earth's surface cools rapidly, sometimes in just hours or days. This rapid cooling doesn't give crystals time to grow large. The resulting rock has a fine-grained texture where individual crystals are too small to see without magnification. Basalt, the most common rock forming the ocean floor, forms this way. Sometimes lava cools so rapidly that crystals don't have time to form at all. The result is volcanic glass, like obsidian, with its smooth, glassy texture and sharp edges that ancient peoples fashioned into cutting tools. Occasionally, magma begins cooling slowly underground, forming some large crystals, then erupts and cools rapidly at the surface. The resulting rock shows large crystals embedded in a fine-grained matrix, a texture called porphyritic. This rock records a two-stage cooling history in its very fabric. While igneous rocks form from molten material, sedimentary rocks tell a different story, one of accumulation and burial. The word sedimentary comes from Latin words meaning to settle or to sink down. These rocks form at Earth's surface through processes you can observe in your own lifetime, unlike the slow cooling of magma deep underground. Sedimentary rocks begin with weathering, the breakdown of existing rocks through exposure to wind, water, ice, and chemical reactions. Physical weathering mechanically breaks rocks into smaller pieces. Water seeps into cracks, freezes and expands, wedging the rock apart. Plant roots grow into fissures, gradually forcing them wider. Desert rocks expand and contract as temperatures swing from scorching days to frigid nights, eventually cracking like old paint. Wind hurls sand grains against rock faces, slowly abrading them away. Chemical weathering alters rocks through chemical reactions. Rainwater, slightly acidic from dissolved carbon dioxide, slowly dissolves limestone. Water reacts with minerals in granite, transforming hard feldspars into soft clay minerals. Iron in rocks oxidizes, forming rust that weakens the stone. Over time, solid rock crumbles into soil and sediment. Erosion then transports this sediment. Rivers carry sand and mud toward the sea. Wind blows dust across continents. Glaciers scrape rocks from mountainsides and carry the debris toward lower elevations. Eventually, this sediment accumulates in layers. Sand settles on river deltas and beaches. Mud accumulates on the ocean floor. Shells and skeletons of countless marine organisms rain down through the water column, building thick deposits of calcium carbonate on the seafloor. As layer upon layer of sediment accumulates, the weight compresses the lower layers. Water is squeezed out. Minerals dissolved in water precipitate in the spaces between grains, cementing them together. Over time, measured in millions of years, loose sediment transforms into solid sedimentary rock. Sandstone forms from ancient sand dunes or beaches. Shale develops from mud that settled in quiet water. Limestone builds from the accumulated calcium carbonate shells and skeletons of marine life. Sedimentary rocks often preserve features that reveal the conditions when they formed. Ripple marks from ancient streams or beaches appear on bedding plains. Mud cracks suggest the sediment periodically dried out. Fossils, the preserved remains or traces of ancient life, occur almost exclusively in sedimentary rocks. These fossils provide windows into Earth's biological past, showing us worlds of trilobites, dinosaurs, and primitive plants that vanished millions of years ago. The third major rock type, metamorphic rocks, forms when existing rocks are transformed by heat, pressure, or chemically active fluids without actually melting. The word metamorphic comes from Greek roots meaning change and form. These rocks tell stories of burial deep within Earth's crust, of continental collisions that squeeze and heat rocks, of magma chambers that bake surrounding stone. Temperature and pressure both increase with depth inside Earth. Rocks buried deep beneath accumulating sediments or pushed down during mountain building may reach depths where temperatures exceed several hundred degrees Celsius, and pressures reach thousands of times atmospheric pressure at sea level. Under these conditions, minerals become unstable. Their atoms rearrange into new crystal structures better suited to the extreme conditions, transforming the rock without melting it. Shale, formed from ancient mud, transforms under moderate heat and pressure into slate, the rock once widely used for roof tiles and chalkboards. The pressure aligns platy minerals parallel to each other, giving slate its characteristic ability to split into thin sheets. Further metamorphism transforms slate into schist, where the recrystallized minerals become visible as shiny flakes. Even greater heat and pressure produces gneiss, with its distinctive banding of light and dark minerals. Limestone, originally formed from accumulated shells and carbonate sediments, metamorphoses into marble. The calcium carbonate recrystallizes into larger, interlocking crystals, creating the beautiful stone prized by sculptors and builders for millennia. Pure limestone becomes white marble, but impurities create the swirls of color seen in decorative marbles. The rock cycle connects all three rock types in a continuous loop. Igneous rocks, exposed at Earth's surface, weather into sediments that eventually become sedimentary rocks. Burial and heating transform sedimentary rocks into metamorphic rocks. Melting turns any rock type back into magma, which cools to form new igneous rocks. Uplift and erosion can expose any rock type at Earth's surface, starting the cycle again. This cycle operates on timescales that dwarf human experience. A grain of sand might take tens of millions of years to travel from mountain to ocean, be buried and transformed into metamorphic rock, then melted and incorporated into new igneous rock. Yet despite these immense timescales, the cycle is constantly operating. Mountains rise and erode. Sediments accumulate and lithify. Rocks descend into Earth's interior and are transformed or melted. The ground beneath our feet participates in this grand, slow dance of transformation. Minerals, the building blocks. If rocks are the pages of Earth's story, minerals are the letters forming the words. A mineral is a naturally occurring solid crystalline substance with a specific chemical composition and an ordered internal structure. While nearly 5,000 different minerals have been identified, most of Earth's rocks form from combinations of just a handful of common minerals. The key characteristic defining a mineral is its crystalline structure. Atoms in a mineral are arranged in a regular, repeating three-dimensional pattern, like an infinitely extending lattice. This ordered arrangement of atoms determines many of a mineral's properties: how it breaks, how hard it is, what shape its crystals take when they grow freely. Consider quartz, one of Earth's most abundant minerals. Its chemical formula is simple. Silicon dioxide, SiO2, meaning two oxygen atoms bonded to each silicon atom. In quartz, each silicon atom sits at the center of a tetrahedron formed by 4 oxygen atoms. These tetrahedra link together by sharing oxygen atoms, extending in all directions to build a strong, stable structure. This explains why quartz is quite hard, ranking 7 on the Mohs hardness scale, and why it doesn't break along flat planes but instead fractures with curved, shell-like surfaces. Feldspars, the most abundant mineral group in Earth's crust, have more complex compositions. They're silicates, like quartz, but also contain aluminum, calcium, sodium, or potassium. The family includes minerals like orthoclase, potassium feldspar, and plagioclase, sodium-calcium feldspar. Feldspars typically appear pink, white, or gray in rocks, and they rank 6 on the Mohs hardness scale, slightly softer than quartz. Micas represent another important mineral group. These sheet silicates have a layered structure where strong bonds hold atoms together within sheets, but weaker bonds connect the sheets to each other. This structure makes mica easily split into thin, flexible flakes. Muscovite mica appears silvery, while biotite mica is dark brown to black because of iron in its structure. Minerals form through various processes, each leaving its signature in the resulting crystals. When magma cools, minerals crystallize from the melt. The process begins with nucleation, where a few atoms come together and form a tiny crystal nucleus. As the magma continues cooling, more atoms attach to these nuclei and the crystals grow. The cooling rate determines crystal size. Rapid cooling produces microscopic crystals. Slow cooling allows large crystals to develop. Minerals also precipitate from water solutions. When water evaporates from a mineral-rich solution, the dissolved substances become increasingly concentrated until they reach supersaturation and begin crystallizing. Halite, or table salt, forms this way in evaporating seas and salt lakes. Vast salt deposits buried beneath the ground formed when ancient seas dried up, leaving behind thick layers of crystalline minerals. Hot water circulating through rocks can dissolve minerals from one location and deposit them elsewhere. Deep in Earth's crust, water heated by nearby magma or simply by the high temperatures at depth becomes a powerful solvent. As this hydrothermal fluid moves through fractures and pores in rocks, it dissolves minerals along the way. When the fluid cools or its chemistry changes, minerals precipitate out of solution. Spectacular crystal-filled geodes form this way, as mineral-rich water seeps into hollow spaces in rocks and slowly deposits layer upon layer of crystals on the cavity walls. The Cave of Crystals in Mexico contains some of the largest natural crystals ever discovered, massive beams of selenite, a variety of gypsum, up to 11 meters long and weighing dozens of tons. These giants grew over hundreds of thousands of years from mineral-rich water at a constant temperature near 58 degrees Celsius. The perfect conditions for slow, steady crystal growth. Identifying minerals requires examining several characteristics. Luster describes how a mineral's surface reflects light. Metallic luster appears on minerals like pyrite and galena, while quartz shows glassy or vitreous luster, and talc displays a pearly sheen. Color can help identify some minerals, but it's often unreliable because small amounts of impurities can dramatically change a mineral's color. Pure quartz is colorless, but traces of iron produce purple amethyst, while other impurities create pink rose quartz or brown smoky quartz. Streak, the color of a mineral's powder, proves more reliable than surface color. Rubbing a mineral across an unglazed porcelain plate leaves a streak of powder. Hematite, an iron oxide, may appear steel gray, brown, or even red, but its streak is always reddish-brown. Hardness measures a mineral's resistance to scratching. The Mohs hardness scale, developed by German geologist Friedrich Mohs in the early 1800s, ranks minerals from 1 to 10 based on which minerals can scratch which others. Talc, the softest, rates 1 and can be scratched by a fingernail. Diamond, the hardest known natural material, rates 10 and can scratch anything else. Quartz is 7, harder than a steel knife blade but softer than topaz. This scale isn't linear. Diamond is far more than twice as hard as talc. It's actually hundreds of times harder. Crystal habit refers to the characteristic shape a mineral takes. Pyrite often forms perfect cubes or 12-faced pyritohedrons. Quartz typically grows as 6-sided prisms topped with 6-sided pyramids. Calcite commonly appears as rhombohedrons, like squashed cubes. When crystals have space to grow freely, they develop these characteristic shapes, their external form reflecting their internal atomic structure. Cleavage describes how a mineral breaks along flat planes related to its crystal structure. Mica shows perfect cleavage in one direction, splitting into thin sheets. Calcite has 3 cleavage directions, breaking into rhombohedral fragments. Minerals without cleavage, like quartz, display fracture instead, breaking with irregular surfaces. Some minerals show special properties useful for identification. Calcite dissolves vigorously when touched by dilute hydrochloric acid, producing carbon dioxide bubbles. Magnetite, as its name suggests, is magnetic. Some minerals, including certain fluorites and calcites, glow in vivid colors under ultraviolet light, a property called fluorescence. The minerals making up Earth's rocks aren't randomly distributed. The planet's most abundant elements determine which minerals can form. Oxygen is the most abundant element in Earth's crust, followed by silicon. Together, they account for nearly 3/4 of the crust's composition by weight. This explains why silicate minerals, built around silicon-oxygen tetrahedra, dominate crustal rocks. Feldspar alone makes up about 60% of continental crust. Quartz, pyroxenes, amphiboles, and micas, together with feldspars, account for the vast majority of rock-forming minerals. Other minerals, while less common, hold tremendous economic or scientific importance. Native metals like gold, silver, and copper occur as minerals. Sulfide minerals including galena, lead sulfide, and sphalerite, zinc sulfide, are major ore minerals. Halite provides salt. Gypsum is used in drywall and plaster. uranium-bearing minerals fuel nuclear reactors. Gemstones like diamond, ruby, sapphire, and emerald are prized minerals whose rarity, beauty, and durability make them valuable. Understanding minerals is fundamental to understanding geology. They're the chemical building blocks from which rocks assemble, the materials that record conditions when they formed, and the substances that contain much of Earth's economic wealth. Deep time and the geological record. One of geology's most profound revelations is the immensity of Earth's age. The planet has existed for about 4.54 billion years, a span of time so vast that human minds struggle to grasp it. John McPhee, a writer exploring geology for a general audience, described deep time as a concept that stretches the human conception of time in a way nothing else does. For most of human history, people dramatically underestimated Earth's age. In 1650, Archbishop James Ussher calculated from biblical genealogies that Earth was created in 4004 BC, making it roughly 6,000 years old. This young Earth view persisted into the 19th century, even as geologists observed evidence suggesting far greater antiquity. James Hutton, an 18th century Scottish farmer and naturalist, recognized that Earth must be enormously old. Studying rock outcrops, Hutton saw sedimentary layers that must have accumulated slowly, hardened into rock, been uplifted and tilted, then eroded away before new sediments accumulated on top of them. Each step required vast amounts of time. Hutton couldn't calculate Earth's age, but he grasped that geological processes operated over time frames that dwarfed human history. He wrote of finding no vestige of a beginning, no prospect of an end, expressing his awe at Earth's apparent antiquity. In the 19th century, geologists developed the principle of uniformitarianism, the idea that geological processes operating today have worked in similar ways throughout Earth's history. Charles Lyell, in his influential work Principles of Geology, argued that the present is the key to the past. If we see rivers depositing sediment today at measurable rates, we can estimate how long ancient sediment layers took to accumulate. If we observe erosion slowly wearing down mountains, we can calculate how long it took to carve valleys and canyons. These calculations suggested Earth must be at least hundreds of millions of years old, far older than biblical chronologies allowed. However, physicists of the era disagreed. Lord Kelvin, one of the 19th century's most respected scientists, calculated how long Earth would take to cool from an initially molten state to its current temperature. His calculations suggested an age of only 20 to 40 million years. Too brief for the slow geological processes geologists observed. The resolution came with the discovery of radioactivity in the late 19th century. Radioactive elements in Earth's interior generate heat, meaning Earth hasn't simply been cooling since its formation but has an internal heat source. This invalidated Kelvin's calculations. Moreover, radioactive decay provided a new tool for measuring time. Radioactive isotopes decay at constant, predictable rates, transforming into different elements. For example, radioactive uranium-238 decays into lead-206 through a series of steps, with a half-life of about 4.5 billion years. A half-life is the time it takes for half of the radioactive atoms in a sample to decay. After one half-life, half the original uranium remains. After two half-lives, 1/4 remains, and so on. By measuring the ratio of parent isotope to daughter isotope in a mineral and knowing the decay rate, scientists can calculate when the mineral crystallized. Different isotope systems work for different age ranges. Carbon-14, with a half-life of only 5,700 years, is useful for dating organic materials up to about 50,000 years old. Perfect for archaeology, but useless for most geological work. Potassium-40, decaying to argon-40 with a half-life of 1.3 billion years, can date rocks hundreds of millions to billions of years old. Uranium-lead dating works for Earth's oldest rocks. Using these techniques, geologists have dated Earth's oldest rocks to about 4 billion years. The oldest known mineral grains, tiny zircon crystals from Western Australia, are 4.4 billion years old. These grains must have eroded from even older rocks that no longer exist. The age of Earth itself, 4.54 billion years, comes from dating meteorites, which formed at the same time as Earth from the same cloud of material orbiting the young sun. Geologists have divided Earth's history into hierarchical units. The largest divisions are eons. Earth's first eon, the Hadean, lasted from Earth's formation until about 4 billion years ago, named after Hades because Earth's surface was likely hellishly hot. The Archean eon followed, lasting until 2.5 billion years ago. The Proterozoic eon extended from 2.5 billion to 541 million years ago. We currently live in the Phanerozoic eon, which began 541 million years ago and continues today. Phanerozoic means visible life, because this eon has left abundant fossils, unlike earlier times when life was mostly microscopic. Eons divide into eras, eras into periods, and periods into epochs. The Phanerozoic eon includes 3 eras: Paleozoic, ancient, life; Mesozoic, middle life; and Cenozoic, recent life. The Mesozoic era, from 252 to 66 million years ago, is famous as the Age of Dinosaurs. It includes 3 periods: Triassic, Jurassic, and Cretaceous. The Cenozoic era, from 66 million years ago to today, saw mammals diversify after dinosaurs went extinct. This geological timescale wasn't built through radioactive dating alone. Before radiometric methods existed, geologists constructed a relative timescale by studying rock layers and fossils. The principle of superposition states that in undisturbed sedimentary layers, older rocks lie beneath younger ones. By examining fossil assemblages in different layers, geologists recognized that life has changed dramatically through time, and that certain fossils characterize particular time periods. The discovery that fossil assemblages could be used to correlate rocks from different locations was revolutionary. A geologist studying rocks in England could compare their fossils to rocks in North America and determine whether they formed at the same time, even though the rocks looked quite different and were separated by an ocean. This principle of faunal succession allowed construction of a relative geological timescale, decades before anyone could assign absolute ages to the periods. Reading Earth's geological record requires understanding that it's incomplete. Erosion removes rock layers. Tectonic forces deform and destroy rocks. Volcanic activity obliterates what came before. Much of the Precambrian, the first 4 billion years of Earth history, has left only fragmentary records. The further back in time we look, the more gaps appear in the record. Nevertheless, rocks and minerals preserve an astonishing amount of information. Sedimentary rocks reveal past environments. Ancient rivers, beaches, deserts, swamps, and seas. Fossils document the evolution of life from simple single-celled organisms to complex multicellular creatures. Chemical signatures in rocks record changes in atmospheric composition, ocean chemistry, and climate. Radiometric dates anchor events in absolute time. Geology teaches us that Earth is dynamic, always changing, yet these changes occur mostly at rates far too slow for humans to observe directly. Mountains that seem eternal to us are temporary features, rising through tectonic processes, then gradually eroding away over tens of millions of years. Ocean basins open and close over hundreds of millions of years. Continents that are now thousands of kilometers apart once nestled together. The solid rock beneath our feet was once molten magma, or seafloor sediment, or different rock entirely, transformed through the rock cycle. Understanding deep time changes how we see the world. A human lifespan, perhaps 80 years, is about 25 millionths of Earth's age. All of recorded human history, roughly 5,000 years, represents barely more than 1 millionth of Earth's existence. The dinosaurs, which seem ancient to us, didn't appear until Earth was already 4 billion years old, 90% through its current history. They then thrived for about 170 million years, more than twice as long as mammals have been dominant. Humans in our modern form have existed for perhaps 300,000 years, less than 1/10,000th of Earth's age. This perspective is simultaneously humbling and inspiring. Humbling because it reveals how recent and brief our existence has been. Inspiring because the rocks around us connect us to this vast history. Every pebble on a beach participated in the rock cycle. Every mountain represents tectonic forces operating over millions of years. Every crystal in a granite countertop formed from cooling magma, perhaps hundreds of millions of years ago. Geology invites us to see deep time written in the landscape, to recognize that Earth's story is far grander and longer than we initially imagined. Mountains, born from collision. Mountains are Earth's most dramatic geological features, rising kilometers above their surroundings and creating barriers to weather, obstacles to travelers, and sources of inspiration to anyone who has stood in their shadow. Yet mountains aren't permanent features. They're created by tectonic forces, then immediately begin eroding away. The highest mountain ranges visible today are relatively young in geological terms, having risen within the past several tens of millions of years. Mountain building, called orogenesis, occurs through several mechanisms, most involving plate tectonics. The world's highest mountains form at convergent plate boundaries where continental plates collide. When two continental land masses come together, neither subducts easily because continental crust is thick and buoyant. Instead, the collision crumples, thickens, and uplifts the crust, pushing it skyward. The Himalayan mountain range exemplifies this process. About 50 million years ago, India, which had broken away from the ancient supercontinent Gondwana and drifted northward, collided with Asia. The Tethys Sea, which once separated the two land masses, was gradually consumed as oceanic crust subducted beneath Asia. Eventually, continental India reached the subduction zone and rammed into Asia. The collision continues today. India moves northward at about 5 centimeters per year, still pushing into Asia. This ongoing collision has thrust sedimentary rocks that formed on the Tethys seafloor upward to heights of over 8,000 meters. Mount Everest, Earth's highest peak at 8,849 meters above sea level, is built partly of marine limestone, complete with fossils of ancient sea creatures. The presence of these marine rocks at such elevations dramatically illustrates the power of plate tectonics. The collision hasn't just built the Himalayas. It has thickened Earth's crust across a vast region of Central Asia. This thickened crust has uplifted the Tibetan Plateau, a region larger than Western Europe now standing at an average elevation of 4,500 meters. The collision has also caused tectonic stresses that reach far into Asia, triggering earthquakes hundreds of kilometers from the actual plate boundary and possibly contributing to volcanism in regions like eastern China. Other great mountain ranges formed through similar continental collisions. The European Alps rose from the collision between the African and Eurasian plates, a process that began about 65 million years ago and continues today. The Appalachian Mountains in eastern North America and the Caledonian Mountains of Scotland and Scandinavia are older, worn-down ranges that formed about 480 to 300 million years ago, when continents collided during the assembly of Pangaea. Mountains also form at convergent boundaries where oceanic crust subducts beneath continental crust. The Andes Mountains along South America's western coast exemplify this type. As the oceanic Nazca Plate subducts beneath the South American plate, several processes build mountains. The compression from the converging plates deforms and uplifts the continental crust. Additionally, as the subducting slab descends into the hot mantle, water trapped in minerals within the oceanic crust is released. This water lowers the melting point of mantle rock above the slab, triggering melting. The resulting magma, less dense than surrounding rock, rises toward the surface. Some of this magma reaches the surface and erupts, building volcanic mountains. The Andes contain numerous active volcanoes formed this way. Much of the magma, however, solidifies underground, forming large bodies of granite that cool slowly over hundreds of thousands to millions of years. As overlying rocks erode away, these granite bodies eventually become exposed at the surface, forming the cores of many Andean peaks. The Cascade Range in the Pacific Northwest of North America formed through a similar process, as the Juan de Fuca Plate subducts beneath the North American plate. Mount Rainier, Mount Hood, and Mount Shasta are volcanic peaks built from eruptions above this subduction zone. Mount St. Helens spectacularly demonstrated the power of subduction-related volcanism when it erupted in 1980. Not all mountains form at plate boundaries. Hotspots, places where hot mantle rock rises in a plume from deep in Earth's interior, can build mountains in the middle of tectonic plates. The Hawaiian Islands are volcanic mountains built over a hotspot beneath the Pacific Plate. As the plate moves northwestward over the relatively stationary hotspot, a chain of volcanic islands forms, youngest in the southeast where the hotspot currently lies, and progressively older to the northwest. The Big Island of Hawaii is still growing, with active volcanoes adding new land even now. Meanwhile, older islands have moved away from the hotspot and ceased volcanic activity. They now erode slowly, gradually shrinking as tropical weathering and wave action wear them down. Eventually, these volcanic islands erode below sea level, becoming seamounts, underwater mountains that never quite reached the surface or were worn down after their formation. The Pacific Ocean floor is dotted with thousands of seamounts, many of them extinct volcanoes. Once mountains form, erosion immediately begins tearing them down. Water is the primary agent of erosion. Rain falling on slopes runs downhill, gathering into streams that carve valleys. Rivers transport sediment eroded from mountains toward the sea. During ice ages, glaciers form in high mountain valleys, and these rivers of ice are phenomenally effective at erosion. Glaciers pluck rocks from valley walls and floors, then grind them against bedrock, scouring deep U-shaped valleys. When the ice eventually melts, it leaves behind a dramatically altered landscape of steep-walled valleys, sharp peaks, and bowl-shaped cirques where glacier heads once lay. Chemical weathering also attacks mountains. Rainwater, slightly acidic from dissolved carbon dioxide, slowly dissolves limestone and marble. It reacts with minerals in granite and other rocks, transforming feldspars into clay minerals and breaking down the rock's structure. Frost wedging occurs when water in rock cracks, freezes, and expands, forcing the cracks wider. Over countless cycles of freezing and thawing, solid rock breaks apart. The rate of erosion depends on several factors: climate, rock type, and tectonic setting. Mountains in wet tropical climates erode faster than those in dry regions. Soft, sedimentary rocks wear away more quickly than hard granite or metamorphic rocks. Interestingly, the fastest rates of mountain building and the fastest rates of erosion both occur at the same place, where active tectonic uplift continues. As long as tectonic forces lift mountains faster than erosion can remove material, the range continues growing taller. Once uplift slows or stops, erosion gradually reduces the mountains. The Appalachian Mountains illustrate this process. Once comparable in height to the modern Himalayas, when they formed hundreds of millions of years ago, the Appalachians have been eroding for over 250 million years since tectonic activity ceased in that region. Today, the Appalachians' highest peaks barely exceed 2,000 meters, less than a quarter the height of the tallest Himalayan peaks, even though the Appalachians are built on thick, strong continental crust. Mountains profoundly influence climate, ecosystems, and human activities. They create rain shadows. When moisture-laden air rises to cross a mountain range, It cools and loses most of its moisture as precipitation on the windward side, leaving the leeward side dry. The Cascades create a dramatic rain shadow in the Pacific Northwest. Western Washington and Oregon receive heavy rainfall, while eastern portions of these states lie in the mountains' rain shadow and are much drier. Mountains also create distinct climate zones at different elevations. Ascending a tall mountain is like traveling from equator to pole, with temperature dropping about 6 degrees Celsius for every 1,000 meters of elevation gain. This creates ecological zones stacked vertically. Tropical forest at the base might give way to temperate forest, then subalpine meadows, then tundra, and finally permanent snow and ice near the summit. For humans, mountains have been barriers and refuges, sources of water and minerals, and perpetual challenges. Many cultures regard high peaks as sacred. Mountains continue inspiring awe in anyone who contemplates these colossal features built from the restless movements of tectonic plates. Volcanoes, windows to the interior. Few geological phenomena are as spectacular or fearsome as volcanic eruptions. When molten rock from Earth's interior reaches the surface, the results can range from gentle flows of glowing lava to catastrophic explosions that devastate entire regions. Volcanoes provide direct evidence that Earth's interior is hot, at least partially molten, and constantly in motion. Volcanic eruptions occur wherever magma reaches Earth's surface. This happens most commonly at tectonic plate boundaries, but also at hotspots far from plate margins. The style of eruption depends largely on the magma's composition and gas content. Magma composition varies primarily in its silica content. Basaltic magma, relatively low in silica, is hot, fluid, and flows easily. When basaltic magma erupts, it produces relatively gentle, effusive eruptions where lava flows across the landscape. Hawaiian volcanoes typify this style. Lava fountains, hundreds of meters high, spray molten rock into the air, and rivers of glowing lava flow down the volcano's flanks toward the sea. While such eruptions can destroy property, they rarely kill people because the lava moves slowly enough that people can evacuate. At the other extreme, rhyolitic magma has high silica content. This makes it thick, viscous, and resistant to flow, like cold honey. High silica magma also tends to contain abundant dissolved gases. As magma rises toward the surface, pressure decreases and gases come out of solution, like carbon dioxide fizzing from an opened soda bottle. In fluid basaltic magma, gas bubbles can escape easily. In thick rhyolitic magma, gas bubbles can't escape readily. Pressure builds until the magma literally explodes, fragmenting into ash and pumice that blast high into the atmosphere in explosive eruptions. The 1980 eruption of Mount St. Helens in Washington demonstrated the power of explosive eruptions. The volcano, which had been dormant for over a century, awoke with earthquakes and small eruptions in March 1980. By May, a large bulge had formed on the mountain's north flank as magma intruded into the volcano. On the morning of May 18th, an earthquake triggered, a massive landslide that removed the bulge, suddenly releasing pressure on the magma system. The depressurized magma exploded laterally, generating a blast that knocked down every tree within an area of about 230 square miles. Ash blasted 50,000 feet into the stratosphere. 57 people died despite extensive monitoring and evacuation orders. The eruption removed over a cubic kilometer of material from the mountain, reducing its height by about 400 meters and leaving a horseshoe-shaped crater open to the north. Lahars, volcanic mudflows formed when hot ash and pumice mixed with melted snow and ice swept down valleys surrounding the volcano, destroying bridges and structures. The eruption injected massive amounts of ash into the atmosphere, causing measurable global cooling for several years. Mount St. Helens illustrated the hazards of subduction zone volcanoes. All around the Pacific Ocean, the Ring of Fire hosts hundreds of active volcanoes formed above subduction zones. These volcanoes tend to have explosive potential because the magmas feeding them are relatively silica-rich and gas-rich. In contrast, Hawaiian volcanoes rarely explode violently because their basaltic magmas are more fluid and gas-poor. The islands themselves are built from countless lava flows that have accumulated over hundreds of thousands to millions of years. Kilauea volcano on Hawaii's Big Island has been erupting almost continuously since 1983, adding new land to the island as lava flows reach the sea and cool into new rock. The Hawaiian Islands illustrate another characteristic of hotspot volcanoes: their progressive age pattern. The Big Island hosts active volcanoes currently positioned over the hotspot. Moving northwest along the island chain, the islands get progressively older. Kauai, about 5 million years old, shows no recent volcanic activity and has been heavily eroded into spectacular valleys and cliffs. Even farther northwest, ancient volcanic islands have eroded entirely below sea level, leaving only underwater seamounts to mark where islands once stood. Not all volcanoes form mountains. At mid-ocean ridges, basaltic magma erupts along the spreading center. But because it erupts underwater, it forms new ocean floor rather than towering peaks. These eruptions occur almost continuously, but go unnoticed because they're hidden beneath thousands of meters of seawater. Over time, these submarine eruptions create the entire ocean floor, making underwater volcanism more voluminous than all terrestrial volcanism combined. Some of Earth's most catastrophic eruptions created features called calderas. Massive depressions formed when a magma chamber empties and the overlying ground collapses into the void. Crater Lake in Oregon occupies a caldera formed about 7,700 years ago when Mount Mazama erupted and then collapsed. The eruption ejected roughly 50 cubic kilometers of material, spreading ash across what is now western North America. Even larger eruptions, called supereruptions, have occurred in Earth's past. Yellowstone National Park sits atop a massive volcanic system that has produced 3 supereruptions in the past 2.1 million years. The most recent about 640,000 years ago. That eruption ejected approximately 1,000 cubic kilometers of material, creating a caldera about 45 by 80 kilometers across. Smaller eruptions and lava flows have since partially filled the caldera, but the region remains volcanically active, as evidenced by geysers, hot springs, and measurable ground deformation. Volcanic eruptions affect more than just the immediate vicinity. Large eruptions inject ash and sulfur dioxide into the stratosphere, where sulfur dioxide reacts with water to form sulfate aerosols. These aerosols reflect sunlight back into space, cooling Earth's surface. The 1815 eruption of Mount Tambora in Indonesia ejected so much material into the stratosphere that global temperatures dropped by about 1 degree Celsius the following year, making 1816 the year without a summer in many regions. Crop failures caused widespread famine in Europe and North America. Despite their hazards, volcanoes provide benefits. Volcanic soil is extremely fertile because fresh volcanic rock weathers rapidly, releasing nutrients. Many densely populated agricultural regions, from Java to the slopes of Mount Vesuvius, thrive despite volcanic risk because the soil is so productive. Volcanoes also create geothermal energy resources. Iceland harnesses volcanic heat to generate electricity and warm buildings. The Philippines, Indonesia, Japan, and other volcanic regions increasingly tap geothermal energy. For geologists, volcanoes are laboratories revealing Earth's interior. Volcanic rocks provide samples of material from depths too great to drill. Gases emitted from volcanoes sample the volatiles present in magma and Earth's interior. Volcanic tremors and earthquakes reveal how magma moves underground. Each eruption adds to our understanding of the powerful forces operating beneath Earth's thin crust. Earthquakes, the restless Earth. The ground beneath our feet seems solid and stable, yet Earth's crust is constantly shifting, accumulating stress, and occasionally releasing that stress suddenly in earthquakes. These seismic events remind us that we live on a dynamic, geologically active planet. Earthquakes occur when rocks under stress suddenly rupture and slip along faults. Fractures where movement has occurred. Stress accumulates because tectonic plates move constantly, but friction prevents smooth, continuous motion along faults. Instead, the rocks along a fault lock together. As the plates continue trying to move, stress builds in the locked rocks, deforming them like a slowly bent stick. Eventually, the stress exceeds the rock's strength. The fault ruptures. The rocks spring back to their original shape in a process called elastic rebound, and the stored energy releases as seismic waves that radiate outward through Earth. Most earthquakes occur along plate boundaries, where tectonic stresses are greatest. At convergent boundaries, compression stress causes earthquakes on thrust faults, where one block of rock moves up and over another. The strongest earthquakes ever recorded have occurred at subduction zones, where one plate slides beneath another. The 1960 earthquake in Chile, the most powerful earthquake measured to date, registered magnitude 9.5 on the moment magnitude scale, the modern measure of earthquake size. The quake ruptured roughly 1,000 kilometers of the fault zone where the Nazca Plate subducts beneath South America. Transform boundaries, where plates slide horizontally past each other. Produce another category of destructive earthquakes. California's San Andreas Fault. Marking the boundary between the Pacific and North American plates has generated numerous major earthquakes. The 1906 San Francisco earthquake, roughly magnitude 7.9, ruptured about 470 kilometers of the fault. The shaking destroyed most of San Francisco's buildings, and fires started by broken gas lines burned much of what remained standing. Divergent boundaries at mid-ocean ridges also experience earthquakes, but these are generally smaller and cause no damage because they occur far from land. Continental rift zones, however, can produce damaging earthquakes. The East African Rift experiences frequent seismic activity as the African continent slowly splits apart. Not all earthquakes occur at plate boundaries. Intraplate earthquakes happen within plates, far from plate edges. Their causes are sometimes mysterious, but they can be quite destructive because people living far from plate boundaries often aren't prepared for seismic activity. The New Madrid seismic zone in the central United States produced a series of powerful earthquakes in 1811 and 1812 estimated at magnitudes 7.5 or greater. These earthquakes rang church bells in Boston, over 1,600 kilometers away, and temporarily reversed the flow of the Mississippi River. The region remains seismically active today, though large earthquakes there are rare. Human activities can also trigger earthquakes. Filling large reservoirs behind dams loads the crust with enormous weight, potentially triggering earthquakes on pre-existing faults. Injecting fluids underground, whether for oil and gas extraction or for wastewater disposal, can increase pore pressure in rocks, effectively lubricating faults and making them more likely to slip. Oklahoma experienced a dramatic increase in earthquake frequency starting around 2009, coinciding with increased underground injection of wastewater from oil and gas operations. When an earthquake occurs, it generates several types of seismic waves that propagate through Earth. P waves, or primary waves, are compressional waves similar to sound waves. They travel fastest and arrive first at distant seismometers. S waves, or secondary waves, are shear waves that arrive after P waves. S waves can't travel through liquid, a property that helped reveal Earth has a liquid outer core. Surface waves travel along Earth's surface and often cause the most damage because they produce strong ground motion. Seismometers detect and record these waves. By analyzing seismic records from multiple stations, seismologists can determine an earthquake's location and magnitude. The difference in arrival times between P waves and S waves reveals how far away the earthquake occurred. By triangulating from at least 3 seismometer stations, the precise location can be pinpointed. Earthquake magnitude quantifies the energy released. The original Richter scale, developed in 1935, worked well for local earthquakes in California, but had limitations for larger, distant, or different types of earthquakes. Modern seismology uses the moment magnitude scale, which more accurately measures very large earthquakes and is based on the amount of slip on a fault, the area of the fault that ruptured, and the rigidity of the rocks. The magnitude scale is logarithmic. Each whole number increase represents about 30 times more energy released. A magnitude 7 earthquake releases roughly 1,000 times more energy than a magnitude 5 earthquake. The largest recorded earthquakes around magnitude 9 to 9.5, release energy equivalent to thousands of nuclear weapons. Earthquake intensity measures the severity of shaking and damage at particular locations, as distinct from magnitude, which measures total energy. The modified Mercalli intensity scale uses Roman numerals from I to 12. Intensity 1 is imperceptible shaking felt by almost no one. Intensity 5 is strong enough to wake sleepers and knock pictures from walls. Intensity 9 causes considerable damage to well-built structures. Intensity 12 represents total destruction. Earthquake hazards extend beyond ground shaking. Liquefaction occurs when waterlogged sediments shake so violently that they temporarily behave like liquid rather than solid ground. Buildings constructed on liquefied ground may tip over or sink. The 1989 Loma Prieta earthquake near San Francisco caused extensive liquefaction damage in areas built on loose sediment fill. Landslides triggered by earthquakes can be catastrophic. In 1970, a magnitude 7.9 earthquake in Peru triggered an avalanche from Mount Huascaran that buried the towns of Yungay and Ranrahirca, killing an estimated 22,000 people. Tsunamis, often miscalled tidal waves despite having nothing to do with tides, are perhaps the deadliest earthquake hazard. When an earthquake occurs under the ocean and vertically displaces the sea floor, it sets in motion waves that can cross entire ocean basins. In the open ocean, tsunami waves have huge wavelengths but small amplitudes, often passing beneath ships unnoticed. As they approach shore and enter shallow water, the waves slow down, their wavelengths shorten, and their amplitudes increase dramatically, sometimes creating walls of water tens of meters high. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake off Sumatra, killed over 230,000 people around the Indian Ocean basin. The 2011 earthquake off Japan's coast generated a tsunami that killed nearly 20,000 people and caused the Fukushima nuclear disaster. Predicting earthquakes remains one of geology's most challenging problems. Scientists can identify regions at high risk based on plate boundary locations and the history of past earthquakes. They can sometimes detect precursors like changes in groundwater levels, release of radon gas, or alterations in ground elevation. However, reliably predicting exactly when and where an earthquake will strike remains beyond current capabilities. Instead, earthquake preparedness focuses on forecasting probabilities. The United States Geological Survey estimates there's a 75% chance of a magnitude 7 or greater earthquake striking the San Francisco Bay Area before 2043. This doesn't tell us the specific date, but it informs building codes, emergency preparedness planning, and public education. Engineering solutions can significantly reduce earthquake damage. Buildings designed to withstand shaking, with flexible frames that sway rather than collapse, fare much better than rigid structures. Base isolation systems place buildings on bearings that allow the ground to shake, while the building remains relatively still. Retrofitting older structures with steel bracing or other reinforcement can prevent collapse. Countries like Japan and New Zealand, located on active plate boundaries, have invested heavily in earthquake-resistant construction and have consequently reduced casualties despite experiencing frequent strong earthquakes. Earthquakes remind us that Earth is geologically active. The very processes that make our planet dynamic and habitable, plate tectonics driving volcanic activity and building mountains, also produce these destructive seismic events. Understanding earthquakes helps us prepare for them and minimize their impact, but it also deepens our appreciation for the immense forces constantly reshaping our planet. Erosion and weathering. Sculpture of landscapes. While tectonic forces build mountains and create new crust, erosion and weathering work ceaselessly to break down rocks and reshape Earth's surface. These destructive processes balance the constructive forces, ensuring that mountain ranges don't grow infinitely tall and that Earth's surface constantly renews itself through the rock cycle. Weathering is the breakdown of rocks in place without transportation of material. It operates through physical and chemical mechanisms, often working together to disintegrate even the hardest rocks given sufficient time. Physical weathering, also called mechanical weathering, breaks rocks into smaller pieces without changing their chemical composition. Frost wedging is one of the most effective mechanisms. Water seeps into cracks in rocks, and when temperatures drop below freezing, the water turns to ice. Ice occupies about 9% more volume than liquid water. So, freezing water exerts tremendous pressure on the surrounding rock, forcing cracks wider. After countless freeze-thaw cycles, solid rock breaks into angular fragments. This process is particularly effective in regions with frequent temperature fluctuations around freezing, such as high mountains and high latitudes. Thermal expansion and contraction can also fracture rocks. Desert rocks expand slightly when heated by intense sunlight, then contract as they cool during cold nights. Over time, this repeated expansion and contraction can cause surface layers to peel away in a process called exfoliation, like layers of an onion separating. Large granite domes, like those in Yosemite National Park, show exfoliation where massive, curved sheets of rock separate from the underlying bedrock. Salt crystal growth provides another physical weathering mechanism. In arid regions or along coastlines, salt water enters rock pores. As the water evaporates, salt crystals grow, and as they grow, they exert pressure that can pry apart mineral grains and widen cracks. Archaeological sites in dry climates often show stone carvings damaged by salt weathering. Plant roots contribute to physical weathering as they grow into rock cracks, gradually forcing them wider. Even tree roots can, over years, break apart large rocks. You can often see trees growing from cracks in cliffs or boulders, their roots slowly wedging the rock apart. Unloading or pressure release causes fracturing when deeply buried rocks are brought to the surface through erosion of overlying material. The reduction in pressure allows the rocks to expand slightly, causing fractures roughly parallel to the surface. This contributes to the formation of exfoliation features in granitic rocks. Chemical weathering alters rocks through chemical reactions, changing minerals into different substances. Water plays a central role in nearly all chemical weathering processes, making chemical weathering most effective in warm, wet climates. Dissolution occurs when minerals dissolve in water, Halite, salt, dissolves easily in water, which is why salt deposits only preserve where they are protected from rainfall. Calcite, the primary mineral in limestone, dissolves slowly in pure water, but dissolves much faster in acidic water. Rainwater naturally contains dissolved carbon dioxide from the atmosphere, making it slightly acidic. This weakly acidic water can, over time, dissolve massive amounts of limestone, creating spectacular cave systems. Mammoth Cave in Kentucky, the world's longest known cave system with over 650 kilometers of mapped passages, formed as mildly acidic groundwater dissolved limestone over millions of years. Stalactites hanging from cave ceilings and stalagmites growing up from cave floors form when calcium carbonate, dissolved from limestone in one location, precipitates from water dripping in the cave. On the surface, dissolution of limestone creates karst topography, characterized by sinkholes, disappearing streams, and caves. As limestone dissolves underground, caverns form. When the roof of a near-surface cavern collapses, it creates a sinkhole. In extreme cases, karst regions become landscapes of towering limestone pillars separated by deep channels, like the spectacular karst formations in southern China. Oxidation occurs when oxygen reacts with minerals. Iron in rocks combines with oxygen to form iron oxides, essentially rust. This gives weathered rocks containing iron a reddish or brownish color. Many red rocks, like the famous formations in Utah's Canyon Country, owe their color to iron oxides formed through oxidation of iron-bearing minerals in the rock. Hydrolysis involves chemical reactions between minerals and water. Feldspars, among Earth's most abundant minerals, are quite stable in igneous and metamorphic rocks, but break down through hydrolysis when exposed to water at Earth's surface. Water reacts with feldspars to form clay minerals, which have different crystal structures and chemical compositions than feldspars. This is one reason why granite, composed largely of feldspars and quartz, weathers to produce clay-rich soil. Biological activity enhances chemical weathering. Plant roots release organic acids that help break down minerals. Lichens growing on rock surfaces produce acids that etch the rock. Burrowing animals mix soil, bringing fresh rock fragments to the surface where they are exposed to further weathering. Even bacteria participate, some species accelerating the weathering of particular minerals. The rate of weathering depends on several factors: rock type, climate, and time. Limestone weathers much faster than granite in humid climates. Chemical weathering proceeds fastest in warm, wet environments and slowest in cold, dry conditions. Physical weathering dominates in cold regions with frequent freeze-thaw cycles or in dry regions with large temperature fluctuations. Time is crucial. Given enough time, even the most resistant rocks eventually break down. While weathering breaks rocks apart, erosion transports the resulting material. Water, ice, wind, and gravity all serve as erosional agents, each creating distinctive landscapes. Running water is Earth's dominant erosional agent. Rivers and streams carve valleys, transport sediment, and reshape landscapes. A river's erosive power depends on its velocity, volume, and the nature of the material it's flowing over. Fast-moving water can move larger particles than slow-moving water. Turbulent flow is more erosive than smooth flow. Rivers erode through several mechanisms. Hydraulic action occurs as flowing water pries loose rocks and sediment. Abrasion happens as sediment particles carried by the river scour the riverbed and banks like sandpaper. Dissolved minerals removed through chemical weathering are carried away in solution. Over time, rivers carve deep valleys and transport enormous amounts of sediment. The Grand Canyon illustrates river erosion's power. The Colorado River has carved a canyon over 1,600 meters deep through multiple rock layers, exposing nearly 2 billion years of Earth history in the canyon walls. This erosion occurred over roughly 5 to 6 million years, since the Colorado River established its current course through the region. Glaciers, rivers of ice, are phenomenally effective erosional agents despite moving much slower than water. Ice doesn't erode through hydraulic action but through plucking and abrasion. As glacial ice moves over bedrock, it freezes onto rock fragments, plucking them from the bedrock and carrying them along. Rocks embedded in the ice base scrape against bedrock like coarse sandpaper, polishing and scratching the surface. These scratches, called glacial striations, indicate the direction of ice flow. Glaciers carve distinctive landforms. Valley glaciers transform V-shaped river valleys into U-shaped glacial valleys with steep walls and flat floors. At valley heads, glaciers carve bowl-shaped depressions called cirques. When glaciers retreat, they leave behind moraines, ridges of sediment deposited at the ice margin. Drumlins, streamlined hills, and eskers, winding ridges of sediment, are depositional features created by glaciers. During ice ages, continental ice sheets, thousands of meters thick, covered vast areas. The most recent ice age peaked about 20,000 years ago, when ice sheets covered most of Canada, northern United States, northern Europe, and parts of Asia. These ice sheets scoured the landscape, removing soil, plucking bedrock, and depositing sediment across vast areas. The Great Lakes of North America occupy basins carved by glacial erosion. Wind erosion operates primarily in dry regions with sparse vegetation. Wind can't move large rocks, but it effectively transports sand and dust. Wind-blown sand abrades rocks, creating ventifacts. Rocks with flat, polished faces carved by sandblasting. Wind deflation removes fine sediment, sometimes creating blowouts, depressions in the land surface. Where sand accumulates, it forms dunes that migrate downwind as wind moves sand grains from the windward side to the leeward side. During ice ages, vast areas lacking vegetation were sources of wind-blown dust. This dust, called loess, accumulated in thick deposits downwind of glaciated areas. Some loess deposits in China exceed 100 meters thick. Loess forms extremely fertile soil, supporting productive agriculture in regions like China's Loess Plateau and the American Midwest. Mass wasting refers to the downslope movement of rock and soil under gravity, without a transporting medium like water or ice. It includes everything from slow soil creep to catastrophic rock avalanches. Landslides occur when slopes become unstable. Factors contributing to instability include steep slopes, water lubricating, potential failure surfaces, earthquakes shaking slopes, undercutting of slopes by rivers or waves, and removal of vegetation that helps stabilize soil. Different types of mass wasting include rock falls, where rocks detach from cliffs and fall; slides, where coherent blocks of rock or soil slide along failure surfaces; flows, where material moves like a viscous fluid; and slumps, where material rotates as it slides. Debris flows and mudflows can be catastrophic. When slopes saturated with water fail, the mixture of water and sediment flows downhill like wet concrete, capable of destroying everything in its path and traveling tens of kilometers from its source. Volcanic mud flows, called lahars, form when volcanic ash mixes with water from melted snow, heavy rain, or displaced lake water. Lahars from Nevada del Ruiz in Colombia in 1985 killed over 23,000 people when they swept through valleys and buried the town of Armero. Erosion and weathering work in concert with tectonic processes to shape Earth's surface. Mountains rise through tectonic forces, then erosion immediately begins wearing them down. The sediment eroded from mountains accumulates in basins, eventually lithifying into sedimentary rocks that may later be uplifted and eroded again, continuing the rock cycle. Without erosion, Earth would look radically different, with mountain ranges growing ever higher and valleys never forming. The balance between uplift and erosion creates the varied and beautiful landscapes we see around us. Fossils. Life preserved in stone. Fossils are the preserved remains or traces of ancient organisms, windows into vanished worlds that reveal how life has evolved over Earth's vast history. While most organisms decay completely after death, under certain conditions, parts of organisms or evidence of their existence can be preserved for millions of years. Fossilization requires specific conditions. Most organisms decompose rapidly after death, broken down by bacteria, scavengers, and weathering. For fossilization to occur, remains must be buried quickly, usually by sediment, protecting them from scavengers and the atmosphere. Minerals then gradually replace organic material, turning once living tissue into stone. The most common fossils are hard parts like shells, bones, and teeth. These already mineralized structures resist decay better than soft tissues. When buried in sediment, minerals dissolved in groundwater percolate through the remains. These minerals precipitate in the pore spaces and may gradually replace the original material. The result is a stone replica that preserves the original structure's form, sometimes in exquisite detail. Permineralization occurs when minerals fill empty pore spaces in organic material without replacing the original substance. Petrified wood forms this way. When trees are buried by volcanic ash or sediment, mineral-rich water flows through the wood, depositing minerals like silica in the cells. The wood's cellular structure is preserved in stone, sometimes so perfectly that growth rings and cellular details remain visible under a microscope. Molds and casts form when an organism buried in sediment decays completely, leaving a cavity shaped like the organism. This cavity is a mold. If minerals or sediment later fill the cavity, they form a cast, a replica of the organism's external shape. Carbonization preserves organisms as thin carbon films. When organisms are compressed in sediment, pressure and heat drive off liquids and gases, leaving behind carbon. This process can preserve delicate structures like leaves, ferns, and sometimes even soft-bodied animals. Many plant fossils are preserved as carbonized impressions in sedimentary rocks. Trace fossils preserve evidence of organisms' activities rather than the organisms themselves. Footprints, burrows, feeding traces, and even fossilized dung, coprolites, provide information about ancient organisms' behavior. Dinosaur trackways show how these extinct reptiles moved. Burrows reveal where ancient marine worms or arthropods lived and fed. Trace fossils can provide insights into behavior that body fossils cannot. Extraordinary preservation occasionally occurs in special environments. Insects trapped in tree resin are preserved when the resin hardens into amber. Some specimens are so well preserved that cellular structures and even DNA fragments survive. The La Brea tar pits in Los Angeles trapped thousands of animals in sticky asphalt over the past 40,000 years. Their bones, including those of saber-toothed cats, dire wolves, and mammoths, are preserved in remarkable abundance. Frozen remains occasionally preserve extinct animals with soft tissues intact. Woolly mammoths frozen in Siberian permafrost sometimes retain hair, skin, and internal organs. These finds provide unprecedented information about extinct species' anatomy and physiology. Fossils tell us about evolution, showing how life has changed through time. The fossil record documents the appearance of new groups, the first animals with hard shells appearing about 540 million years ago, plants colonizing land around 470 million years ago, the first vertebrates moving onto land about 370 million years ago, dinosaurs dominating terrestrial ecosystems from about 230 to 66 million years ago. The fossil record also shows mass extinctions, times when large percentages of species disappeared in geologically brief periods. The most famous mass extinction occurred 66 million years ago, ending the Cretaceous period. This event, caused by an asteroid impact and possibly massive volcanism, eliminated non-avian dinosaurs and about 75% of all species. The impact crater, called Chicxulub, lies buried beneath Mexico's Yucatan Peninsula. Evidence for the impact includes a thin layer of iridium-rich clay found worldwide in rocks of that age. Iridium is rare in Earth's crust but common in asteroids, and the global layer suggests an impact scattered pulverized asteroid material worldwide. Other mass extinctions mark the fossil record. The Permian-Triassic extinction about 252 million years ago was even more severe, eliminating roughly 96% of marine species and 70% of terrestrial vertebrate species. Its causes remain debated but may involve massive volcanic eruptions in Siberia, climate change, and ocean chemistry changes. Between mass extinctions, evolution fills ecological niches vacated by extinct species. Mammals, which lived as small, mostly nocturnal creatures during the age of dinosaurs, diversified rapidly after dinosaurs went extinct, eventually producing everything from whales to elephants to humans. Fossils also inform us about ancient environments and climates. Coral reefs only grow in warm, shallow, clear water, so fossil coral indicates tropical marine conditions. Coal forms from accumulated plant remains in swamps, revealing where warm, wet climates existed. Fossil leaves with smooth edges suggest tropical climates, while leaves with serrated edges indicate cooler temperate conditions. Glacial deposits containing scratched rocks and unsorted sediment indicate ancient ice sheets. The distribution of identical fossils on now separated continents provided crucial evidence for continental drift. The small reptile Mesosaurus appears in freshwater deposits in Brazil and South Africa, but nowhere else. It couldn't have crossed the Atlantic Ocean. The simplest explanation is that South America and Africa were connected when Mesosaurus lived, about 290 million years ago, and have since drifted apart. Fossils allow geologists to determine rocks' relative ages. The principle of fossil succession states that fossil assemblages change through time in a characteristic way. Once this succession is established, geologists can identify a rock's approximate age by examining its fossils. This biostratigraphy was geology's primary dating tool before radioactive dating techniques became available and remains useful today. Some fossils, called index fossils, are particularly valuable for dating rocks. Good index fossils existed for relatively brief periods, but were geographically widespread. Trilobites, extinct marine arthropods, are excellent index fossils for Paleozoic rocks. Different trilobite species characterize different time periods, allowing precise age determination. Despite the wealth of information fossils provide, the fossil record is incomplete. Most organisms never fossilize. Soft-bodied creatures rarely leave fossils unless preserved under exceptional conditions. Organisms living in environments where rapid burial is uncommon, like mountain forests, seldom fossilize. Erosion destroys many fossils before scientists find them. Nonetheless, the fossils discovered so far provide an amazing archive of Earth's biological history, revealing the pageant of life across more than 3 billion years. Earth's hidden treasures. Beneath Earth's surface lie concentrations of minerals and elements that human civilization depends upon. These economic mineral deposits form through geological processes that concentrate otherwise dispersed materials into exploitable amounts. Understanding how these deposits form helps geologists locate new resources and reveals another aspect of how our planet works. Ore deposits are rock bodies containing one or more valuable minerals in economically extractable concentrations. The word ore specifically refers to rock from which metals or valuable minerals can be profitably extracted. What qualifies as ore depends on both the material's concentration and economic factors like metal prices and extraction costs. A deposit that wasn't economically viable when metal prices were low might become profitable if prices rise. Many ore deposits form through igneous processes. When magma cools, minerals crystallize in a specific sequence. Some minerals crystallize and sink to the magma chamber's bottom before the rest of the magma solidifies, forming layers of concentrated ore minerals. The Bushveld complex in South Africa, a massive layered intrusion, contains the world's largest reserves of platinum group metals, chromium, and vanadium, all concentrated through this process. Some ore minerals crystallize from the last remaining magma after most minerals have already formed. This late-stage magma can be extremely enriched in elements that didn't fit into earlier formed minerals. Large crystals can grow from this late-stage magma, forming pegmatites, very coarse-grained igneous rocks. Pegmatites are important sources of lithium, beryllium, tantalum, and rare earth elements used in electronics and batteries. Hydrothermal ore deposits form when hot water circulates through rocks, dissolves minerals, then deposits them elsewhere when the water cools or its chemistry changes. These deposits account for much of the world's copper, gold, silver, lead, and zinc production. At mid-ocean ridges, cold seawater seeps into fractured oceanic crust, is heated by magma beneath the ridge, and rises back to the sea floor. This superheated water, loaded with dissolved minerals, erupts from vents called black smokers. As the hot water mixes with cold seawater, minerals precipitate, building chimney-like structures around the vents and depositing metal sulfides on the seafloor. On continents, hydrothermal fluids associated with magma intrusions deposit ores in surrounding rocks. As magma cools, it releases hot, mineral-rich fluids that flow through fractures in the host rock. These fluids dissolve some minerals and deposit others, creating vein deposits that can be spectacularly rich in gold, silver, copper, or other metals. The famous gold deposits of California's Mother Lode region formed this way. Some ore deposits form through weathering and concentration at Earth's surface. Aluminum ore, called bauxite, forms in tropical climates where intense weathering removes silica and other elements from aluminum-bearing minerals, leaving behind an aluminum-rich residue. Brazil, Australia, and Guinea have large bauxite deposits formed this way. Laterite deposits, similar to bauxite but containing iron instead of aluminum, form through tropical weathering. The distinctive red soils of tropical regions reflect high iron oxide content. When concentrated enough, these deposits become iron ore. Placer deposits form when dense, resistant minerals erode from their source rocks and concentrate in stream or beach sediments. Gold, being both dense and resistant to chemical weathering, often concentrates in placers. The California gold rush of 1849 started with the discovery of gold in a placer deposit at Sutter's Mill. Diamonds, being extremely hard and chemically inert, also concentrate in placers, particularly along the coasts of Namibia and South Africa. Sedimentary processes create other important mineral deposits. Evaporite deposits form when seawater or lake water evaporates, leaving behind salt, gypsum, potash, and other minerals. Some evaporite deposits are hundreds of meters thick, representing the evaporation of ancient seas The Dead Sea and Great Salt Lake are modern examples of evaporite formation in action. Iron ore deposits called banded iron formations are unique to ancient Earth. These distinctive rocks consist of alternating layers of iron-rich and silica-rich minerals. They formed between about 3 and 1.88 billion years ago, when Earth's atmosphere contained little oxygen. Iron dissolved in the oceans precipitated when oxygen-producing cyanobacteria released oxygen through photosynthesis. These deposits, found in Australia, Brazil, and the Lake Superior region of North America, provide most of the world's iron ore. Fossil fuels, coal, oil, and natural gas are organic rather than mineral resources, but they form through geological processes. Coal forms from accumulated plant material in swamps. As plants die and accumulate faster than they decay, they build up layers of organic material. Burial compresses this material, gradually transforming it from peat to lignite to bituminous coal to anthracite, each stage representing greater compression and loss of volatile components. Oil and natural gas form from organic material, mostly marine plankton, buried in sedimentary basins. As sediments bury this organic material deeper, rising temperature breaks down complex organic molecules into simpler hydrocarbon compounds. Oil and gas, being less dense than water, migrate upward through porous rocks until trapped beneath impermeable layers, forming reservoirs. Gemstones are minerals valued for their beauty, rarity, and durability. Diamond, the hardest natural substance, forms under the high pressures found deep in Earth's mantle, over 150 kilometers deep. Volcanic eruptions bring diamonds to the surface in unusual volcanic rocks called kimberlites. Most diamonds are industrial grade, used for cutting and drilling, but a small percentage are gem quality. Corundum, aluminum oxide, is the mineral forming ruby and sapphire. Pure corundum is colorless, but trace elements produce colors. Chromium creates ruby's red color, while iron and titanium produce sapphire's blue. Corundum ranks 9 on the Mohs hardness scale, second only to diamond. Beryl produces several gemstones depending on trace elements. Chromium creates the green of emeralds, while iron produces the blue-green of aquamarines. Quartz varieties include amethyst, purple, citrine, yellow, and rose quartz, pink. Though quartz is common, transparent, richly colored crystals suitable for gems are not. The search for mineral resources drives exploration in remote regions. Geologists use various tools to find deposits. Surface mapping identifies rocks likely to host ores. Geochemical surveys sample soil, stream sediment, or vegetation looking for trace elements indicating buried ore. Geophysical surveys measure variations in Earth's magnetic field, gravity, or electrical conductivity that might indicate ore bodies. Drilling provides the definitive test, allowing direct sampling of buried rocks. Once discovered, extracting minerals requires careful consideration of economic and environmental factors. Mining disturbs landscapes and can contaminate water. Modern mining operations must restore land after extraction and prevent pollutants from entering the environment. The challenge is balancing society's need for mineral resources with environmental protection. Mineral resources are finite. Unlike renewable resources such as sunlight or wind, once an ore deposit is mined, it's gone. Recycling metals reduces demand for new mining. Substituting abundant materials for rare ones extends resources. Improving extraction efficiency allows mining lower-grade ores. These strategies help ensure that future generations will have access to the mineral resources they need. As we reach the end of this gentle journey through geology, let yourself sink deeper into relaxation. Your breathing has slowed. Your body has softened. The stories of Earth's deep time and constant transformation have carried you into a peaceful state of rest. Geology reveals a planet that is dynamic and alive in ways we rarely appreciate in our daily lives. The mountains rising in the distance, seemingly eternal, are temporary features that will erode away over tens of millions of years. The solid ground beneath your feet is moving, carried along by tectonic plates floating on the slowly churning mantle. The rocks we walk upon were once something entirely different, transformed through the rock cycle from igneous to sedimentary to metamorphic and back again over geological time. Every pebble on a beach, every boulder on a mountainside, every grain of sand contains a story. The crystal structure within each mineral reflects the conditions when it formed. The temperature, the pressure, the available elements, the presence or absence of water. The sedimentary layers in canyon walls are pages in Earth's autobiography, recording ancient seas, deserts, rivers, and life forms that lived and died millions of years before humans appeared. Volcanoes and earthquakes, while sometimes destructive, are windows into Earth's interior, reminders that we live on a geologically active planet. The forces that create these dramatic events are the same forces that built the continents, created the ocean basins, and make Earth a dynamic, habitable world rather than a cold, dead sphere like the Moon. Erosion and weathering, working grain by grain, reshape landscapes over time. Mountains rise through tectonic forces, but erosion immediately begins wearing them down. Rivers carve valleys. Glaciers scour bedrock. Wind transports dust across continents. The sediment eroded from mountains accumulates in basins, eventually becoming sedimentary rock that may later be uplifted and eroded again, an endless cycle of transformation. Fossils preserved in sedimentary rocks connect us to deep time, showing us worlds inhabited by trilobites, dinosaurs, and creatures unlike anything alive today. They remind us that life has constantly changed throughout Earth's history, adapting to shifting continents, changing climates, and occasional catastrophic events that eliminated most existing species but opened opportunities for survivors to diversify. The mineral resources we extract from Earth's crust formed through specific geological processes: magma cooling and crystallizing, hot water circulating through cracks in rocks, weathering concentrating elements at the surface, organic material being buried and transformed. Understanding these processes helps us find the materials our civilization depends upon, while also teaching us about Earth's workings. Geology is ultimately about time, deep time that stretches back over 4.5 billion years. Developing a sense of this timescale changes how we see the world. It teaches patience and perspective. It reveals that change, not permanence, is fundamental to Earth. It shows us that our planet has a history far longer than human history. That landscapes we consider eternal have not always existed and will not exist forever in their current forms. Yet geology also has practical applications. Understanding plate tectonics helps us prepare for earthquakes and volcanic eruptions. Knowing groundwater flows helps us manage water resources. Recognizing signs of mineral deposits guides exploration for resources. Reading the geological record helps us understand past climate changes and anticipate future ones. As you drift toward sleep, remember that you're part of this ancient story. The calcium in your bones, the iron in your blood, the oxygen you breathe, all these elements formed in stars that exploded billions of years ago. The atoms in your body have been recycled through countless organisms and geological processes. You are, quite literally, made of stardust and earth. Temporary arrangements of atoms that were here long before you, and will remain long after you're gone, continuing their journey through the rock cycle and the cycles of life. Let this perspective bring you peace. You are connected to everything. To the mountains, to the rivers, to the rocks beneath your feet, to the ancient life forms whose fossils lie buried in stone, to the stars that forged the elements making up your body. You are part of an epic story that began over 4.5 billion years ago and continues into a future beyond imagining. If these quiet explorations of science have brought you comfort tonight, consider returning another time. Consider sharing this channel with others who might appreciate these peaceful journeys through knowledge. Consider subscribing to help these videos reach more people seeking rest and learning in equal measure. Your support helps keep this small corner of calm available for anyone who needs it. But for now, simply rest. Let go of everything. There's nothing you need to do, nowhere you need to be. The night is here. The world will continue its slow geological dance while you sleep. Mountains will rise imperceptibly. Rivers will carry sediment grain by grain toward the sea. Tectonic plates will creep along their paths. The rock cycle will continue its endless transformation. And you can simply rest, carried by the gentle rhythm of these ancient processes into deep, peaceful sleep. Good night.